Hi everybody. The purpose of this video is to go through section 6 of chapter 2, and here we will be talking about logarithmic functions. First, we're going to readdress the idea of one-to-one functions, and then we're going to use that information to define what a logarithmic function is. We will talk about its graph, its properties, how to compute logs on your calculator, and then we will talk a few applications. Okay, so we've talked about one-to-one functions in our previous section. A one-to-one function is that function where each different domain value or each different x value corresponds to a different range value or a different y value. Or, like I said it before, where each different x value produces for you a different y value. Of course, this function right here on the left is the square function. This is not one-to-one because there are two values of x which will produce for you the exact same value of y. For example, -2 and 2 will produce for you 4. Therefore, it is not one-to-one. However, the exponential function y equals 2 to the x, that is a one-to-one function. Different values of x will produce for you different values of y. And as you can see, all exponential functions are indeed one-to-one functions. Now, one of the cool things about a one-to-one function is that they have what we call an inverse, or an inverse function. So let's suppose we have a function, and we're going to call it f, and let's suppose that's a one-to-one function. Well, then the inverse of f is very wittingly called, yeah, you guessed it, the inverse of f. There is also a notation associated with that, but we will talk about that just a little bit later. Okay, now let's suppose that g is the inverse of f. Okay, and further suppose that f evaluated at the number a will produce for you the number b. Well, then if g is the inverse, then g evaluated at the number b will recreate for you the number a. For every a that can be evaluated, for every a that is in the domain of f. Furthermore, if you took a and applied f to it, and then took that result and applied g to it, you will recover a for every value of a that happens to be in the domain of f. Okay, and here's an example. Suppose that we have a linear function 3x plus 2. It happens to be a one-to-one function. All linear functions with a non-zero slope are one-to-one functions. And if that's the case, it has an inverse. And this happens to be the inverse. Don't believe me? Well, check this out. Let's suppose we evaluate f when x is equal to 10. Then we will have 3 times 10 plus 2, which is 32. All right, well, it turns out that if we evaluated g at 32, we will have 32 minus 2 divided by 3, which is 30 divided by 3, which is 10, which recreates 10. Furthermore, so, I was getting ahead of myself. So, f evaluated at 10 is 32, and g evaluated at 32 is equal to 10. And therefore, if I took 10, evaluated at f, I would get 32. And then g of 32 is 10. So I can use basically g to reconstruct whatever the argument of f was. And this brings us to our formal mathematical definition. If f is a one-to-one function, then the inverse of f is formed by interchanging x and y for f. And then solving for y again. Therefore, if a point A and B, the point AB is on the graph of f, then the point BA is on the graph of its inverse. Furthermore, if f is not a one-to-one function, it does not have an inverse. That happens to be a function. And since every exponential function is a one-to-one function, every exponential function has an inverse. And you'll never guess what we're going to call them. Yep, we're going to call them logarithms. Okay, but before we get there, notice here we have the graph of f, the linear function we talked about, and the graph of its inverse. Notice that the point AB, 1032, is on the graph of f. The point 3210 is on the graph of g. Furthermore, notice that this line y equals x basically splits right between the graphs of f and g. So we can say that the graph of f and its inverse will always be symmetric about this particular line. And this brings us up to the idea of a logarithmic function. The inverse of an exponential function with base b, here it is, this is the exponential function of base b, is what we call the logarithmic function. Say that 3 times fast. G of x is equal to the log base b of x. And the way that we figure this out is through the use of what we call equivalent equations. And if you'll bear with me, I'll try to at least walk you through that. Okay, let's do this with an example. Suppose we look at the function y is equal to the x. And furthermore, suppose that we can find the inverse by switching x and y and then solving for y. However, it's kind of hard to get the y out of the exponent, so what we're going to do is we are going to create an inverse function, and we're going to call it the log base 2 of x. And this is what we're going to say. We're going to say that y is equal to log base 2 of x if and only if x is equal to 2 to the y. What the heck am I talking about? Let's take a look at the next slide. Okay, now this is nothing more than a statement that we had in the previous slide. Y is equal to log base 2 of x if and only if x is equal to 2 to the y power. So the question is, what is the log base 2 of 1024? Well, it is going to be that value of y that satisfies the equation, what 2 to the y is equal to 1024. Now it turns out that if y is equal to 10, 2 to the 10th is equal to 1024. Therefore, 10 is equal to the log base 2 of 1024. And we say that the log base, that the equation y equals log base 2 of x and the equation x equals 2 to the y power are equivalent equations because they have the exact same solution set. Specifically, the point 1024, 10, where x is 1024, y is 10, are solutions to both of these equations. And this brings us to our more formal definition of a logarithmic function. The inverse of the exponential function is called the logarithmic function. For any positive b, or b is not equal to 1, then y equals log base b of x is equivalent to the exponential form x is equal to b to the y power. They have the exact same solution sets. And then furthermore, the log to the base b of x, or the logarithm base b of x, is the exponent to which b must be raised to obtain x. And sometimes this is the thinking that we need to go through to figure out what a logarithm of a certain number is for a certain base. And once again, they based on the fact that both y equals log base b of x and x equals b to the y power are equivalent equations and therefore have the same solution sets. The idea here behind this is that maybe this will not make sense to you, but if you write it in the exponential form, not only will it make sense, you will also be able to figure out what y is. And that is what we are going to be doing in our next couple of examples. Specifically, this is going to be an exercise between the equivalence of y is equal to the log base b of x and that x is equal to b to the y. So notice here, each of these are in logarithmic form. This happens to be y. This happens to be x. That happens to be b. And we want to write this in the equivalent exponential form. And while this makes no sense to you, once you write this in the equivalent exponential form, it should make sense to you. For example, here, we have that x, which is 9, is equal to b, which is 3, times 2, which is y. 3 squared equals 9. Of course it does. Makes perfect sense. Now, this is wrong. That should be down here. Sorry about that. Nonetheless, here we have the exact same thing. Y, x, b. So, 2, that's what x is, right, is equal to b, which is 4, raised to the 1/2 power. Okay, and that actually is the square root. The square root of 4 is 2. There you go. Exact same thing here. Y, x, b. And here we have 1/9 is equal to the base, which is 3, raised to the negative 2 power. And of course, that makes sense. You can actually do that in your calculator. Well, you could do this in your calculator, but I need to show you how to do that. Okay, the next example is the same thing, but going in the other direction. Once again, we are going to be using the fact that y equals log base b of x is equivalent with x being equal is equivalent to the equation x equals b to the y power. Here we have the exponential form. We want to write down the logarithmic form. So here we have x, we have b, we have y. So here we have 2 equals to the log base 7 of 49. Here we have the exact same thing. We have y, we have b, we have x. So we have that 1/2 is equal to log base 9 of 3. Okay? And then finally, we have once again y, b, and x. And here we will have that -1 equals the log base 3 of 1/3. Which actually does indeed make sense. Okay, now we can use this property, once again, to find the solutions to certain equations. And that's what we're going to do in these 3 examples. Now, these problems as written probably makes no sense to you, but if you write them in the equivalent exponential form, it will probably make more sense. So let's go ahead and write that down. We have y is equal to the log base b of x, and that's equivalent to x being equal to b to the y power. Okay, so here we would have x, which is 125, is equal to 5 to the y power. And the question is, what must y be so that 5 to the y is equal to 125? Well, if y was 1, you would have 5 to the first power. If y was 2, you would have 5 squared, which is 25. If y is equal to 3, then 5 cubed, well, that actually is 125. Okay, so in this particular case, y must be equal to 3. Okay, for the next one, once again, we have y, we have x, and we have b. And this one actually is very straightforward. The equivalent exponential equation is going to be x is equal to 3 to the -1 power, which, by the way, is just simply 1/3. Okay, for this one, y, x, and there's b, the equivalent exponential form is going to be b cubed is equal to 1,000. Okay, and what value of b when cubed will give you 1,000? In this particular case, it will be that b is equal to 10, because 10 cubed is 1,000. Therefore, b must be equal to 10. So while you usually can't tell in the logarithmic form, the equivalent exponential form might provide you a little bit of insight. This right here is the graph of the logarithmic function. It also has the graph of the exponential function. This is the exponential function x to the x. This is the logarithmic function y of the graph of the log base 2 of x. And this right here is the line y is equal to x. Notice that the graph of the log and the graph of the exponential are reflections across the line y is equal to x, or actually symmetric about that line. And that is one of the main properties of the inverse functions, just like we mentioned when we looked at the graph of those 2 linear equations. Furthermore, notice that the domain for the logarithm is all positive numbers from 0 to infinity, not including 0, of course, which ironically is the range of the exponential function. Furthermore, the range for the logarithm is the entire real line. It goes from negative infinity all the way up to infinity, which ironically is also the domain of the exponential function. And also notice that the exponential function and the log both increase over the entire domain. And also, it is a one-to-one function, which basically means that if the statement log base b of x is equal to log base b of y is true, then x must be equal to y. And if x must be equal to y, then this statement is also true. Okay, with that in mind, let's talk about some of the very useful properties of a logarithm function. Here is the first one. The log base b of 1 is always going to be equal to 0. And that should make sense to you because the equivalent exponential form is going to be b to the 0 is equal to 1. The log base b of b is always equal to 1. That's consistent with b raised to the first power being equal to, you guessed it, b. All right, the log base b of b to the x is equal to x. And the log and b raised to the log base b of x is also x. This is basically a property, this is a consequence of the fact that the log and the exponent are inverses. The exponent and the log are inverses. This property here is called the product property. And this basically says that the log of the product of m and n are basically the sum of their logarithms. This is the quotient property. This says that the log of the quotient of m over n is equal to their difference, log base b of m minus log base b of n. And we have the power property, which says that the log base b of m raised to the p power is equal to p times the log base b of m. And then finally, we have that since the logarithm is a one-to-one function, the log base b of m is equal to log base b of n if and only if m is equal to n. We are going to apply these in the next couple of examples. And here we go. Here's our first one. Here we want to use the logarithmic properties to write these in a simpler form. And once again, we'll be using these properties right here. The first one requires the use of the product property and the quotient property. Applying the quotient property first, you will have that this is equal to the log base b of r minus the log base b of s times t. Now, we can still apply the product property here, and if we do, we will have the log base b of r minus the quantity log base b of s plus the log base b of t. And then we can take this one step forward using the distributive property, and that will give us the log base b of r minus the log base b of s minus the log base b of t. And there you go. That's as far as you can take this. Now, the second problem is going to require a use of the combination of the power property and the quotient property. Now here, we want to use the power property first because we can't really use the quotient property until we get rid of the exponent. So that is going to give us 2/3 times the log base b of r over s. And now we can use the quotient property here. And if we do, we will have 2/3 times the quantity log base b of r minus log base b of s. You could take this one step forward by distributing the 2/3 back in there, and that will give us 2/3 log base b of r minus 2/3 log base b of s. Now for part C, we are going to use a combination of the power property and this particular inverse property. So using the power property, we can rewrite this as 2 to the log base 2 of b to the u power. And then once we've done that, we could then use property 4, which is the inverse property, and then write this as b to the u. Now the last one is a little tricky. And the big thing here is that we actually want to use one of the inverse properties to rewrite x, so that actually has a b in it. So what we're going to do is we are going to take advantage of this particular property right here. That we can rewrite x as b raised to the log base b of x. So let's go ahead and do that. And if I have the log base 2, and I'm going to write x as b raised to the log base b of x. Now, why in the world would I want to do that? Well, notice here that I have b raised to a power. I can use the power property. I can take advantage of the power property right here, and I can take this power and write it as coefficient times the log of m, and that's what I want to do here. Here is my exponent. I can write this as this exponent times the log base 2 of b, and that's exactly what I want to do. So I'm going to have the log base b of x times the log base 2 of b. And over here, I have log base 2 of b. And notice, look what we have here. I have log base 2b on the top, log base 2b on the bottom. They cancel, and I am left with the log base b of x. This is actually a very powerful theorem that we actually call the change of base theorem. Okay, our next example is we want to solve this logarithmic equation, and to do this, we're going to use the properties that we talked about before. Specifically, we are going to use property 5, the product property, this one, and then product 8, the fact that the log is a one-to-one function. Okay, so let's go ahead and do that. The first thing we want to do is the product property, basically to combine these two terms in reverse. So the sum of two logs of the same base can be written as the log of their product. So this can be written as the log base 3 of x times x minus 3, that quantity, is equal to the log base 3 of 10. Now that I have this into the form of the log base 3 of one expression is equal to the log base 3 of another expression, I can take advantage of property 8, the fact that this is a one-to-one function. So if this is true, then x times x minus 3 must be equal to 10. If this is true, then this must be true. All right, so now all I need to do is just solve this equation. Let's go ahead and do that. Using the distributive property, we have x squared minus 3x is equal to 10. Bringing the 10 over, we have x squared minus 3x minus 10 is equal to 0. And now to solve this, we actually had to find factors of negative 10 that sum to negative 5. And one factor that comes to mind, or one set of factors that comes to mind, is negative 5 and positive 2. Negative 5 times 2 is negative 10. Negative 5 plus 2, negative 3. So I can rewrite this as x minus 5 times x plus 2 is equal to 0. And if that's the case, then my proposed solutions are x equals 5 and x equals minus 2. All right, now why are they proposed solutions? Because for them to be valid solutions, these must fall into the domain of the equation. Now, what about so let's take a look at the case when x is equal to negative 2. If I substituted negative 2 back in for x, what I'm going to have is the log base 3 of negative 2 plus the log base 3 of negative 2 minus 3, or negative 5. Okay, negative 2 and negative 5 are outside the domain of the logarithm, so these simply will not work, and negative 2 is not a valid solution. The only valid solution is x is equal to 5, because then you're going to have the log of 5 plus the log of 2, both of which work. So in this particular case, your solution is x is equal to 5. If you included negative 2, this would be marked wrong because negative 2 or x minus or negative 2 minus 3 is not does not fall within the domain of the logarithm. Okay, now we want to talk about frequently used logarithms and their logarithm functions, and there are two, and they are the only two that you'll find on your calculator. They happen to be the common logarithm, which is basically the logarithm base 10, and you can find it using the log button on your calculator. And you'll also find there a button that says 10 to the x, which will be the inverse. The next one is the natural logarithm, which we usually call ln of x. That is the log base e of x, where e happens to be Euler's number, and that is typically computed using the ln button on your calculator. Okay, and this brings us to our next example, and here it is. However, we're not going to do this here. We're going to do this in OneNote, so we can actually see the calculator and the examples and go from there. Okay, so the first one is the common log base 10 of 538,463. Okay, well that's pretty straightforward. We just hit log right there, 538,463, close the parenthesis. You don't have to, hit enter. And our answer is right there. Notice what we have is 5.73115. Those are our 5 decimal places, and the 6th decimal place is a 5. Since the 6th decimal place is 5 or greater, we want to round up, and that will give us 5.73116. Okay, what about the next one? Done the exact same way. No, that's wrong. Log 0.0015765. All right, and that will give us negative 2.80230. All right, and then our 6th decimal place is a 6. And that tells me we need to round up, and that will give us negative 2.80231. Okay, the next two are natural logs. So for those, instead of hitting log, we're going to use the ln button right down here. It knows that the inverse is right there, e to the x. So that's going to be ln, natural log, 258, 8.653, close the parenthesis, enter. And here we have 5.55548. 5.55548. The 6th decimal place is a 7. So this will round to 5.55549. We make that look like a 9. There we go. And then finally, we have the natural log of 0.054357. And that will give me negative 2.912181. And our sixth decimal place is a 1, which is less than 5, so we don't need to round up or down in this case. And that will be approximately equal to negative 2.91218. Here is our next example, solving exponential equations. And here we want to solve x to 4 decimal places. In these problems, we want to find x. And to solve these, what we are going to do is we are going to take the logarithm, specifically the common logarithm of each side, of both sides. So I can rewrite this as the log. So I'm going to take the logarithm here, and I'm going to take the logarithm here. And what I'm going to have is the log of 10 to the x, and this is the common logarithm. This is the common logarithm, so log base 10. And I'm going to take the logarithm of the other side, and that will give me the common log of 7. All right? Now, the log base 10, using the power rule, I'm going to have x times the log base 10, and that's not right. I'm going to have x times the log of 10, the common log of 10, log base 10, is equal to the log of 7. Okay? Now, the log base 10, remember the common log is the log base 10, so the log base 10 of 10 is equal to 1. So this will become x is equal to the log of 7. Okay? And the log of 7, well, log 7, that gives me 0.8450. The fifth decimal place is a 9, so this will round to 0.8451. Okay, so that's part A. Now for B, we're going to do it pretty much the same way. We're going to take the common log of both sides, and that will give me the log base 10 of 4 to the x is equal to the log base 10 of 5. Using the power property on the left-hand side, I will have x times the log base 10 of 4. And that's going to be equal to the log base 10 of 5. Okay, I can now divide both sides by the log base 10 of 4. These will cancel, and I will have that x is equal to the common log of 5 divided by the common log of 4. Okay, since these are ratios of common logs and not logs of a ratio, there's really nothing we can do here. We'll just have to put it in the we'll just have to basically evaluate that. But that's not that big of a problem. Over here, log of 5 divided by log of 4. And that will give me that x is equal to 1.1609. This fifth decimal place is 6. Since that is greater than 5, we will have that x is approximately equal to 1.1610. Since we increment this, when we increment the 9 by 1, we get 10. And that would be the answer for the second part. The third part looks pretty daunting, but we're going to do it the exact same way. We're going to take the the common log of both sides. So we will have the log of 1.886 raised to the 14t power is equal to the common log of 3. Okay, well, and if that's using the power property, we will have 14t times the common log, the common log of 1.886 is equal to the common log of 3. We can divide both sides by 14 times the common log of 1.886. These cancel. All these cancel. I need more space. There we go. And we will have that t is equal to the common log of 3 divided by the product of 14 and the common log of 1.886. Now, working this out in the calculator, you need to be a little careful. The way we're going to do this is log 3, close the parenthesis, divided by, open a parenthesis, because we want to make sure we have the product of this on the denominator, 14 times log 1.886. Close the first parenthesis, close the second parenthesis, and there we go. We get 0.12368. Fifth decimal place is at 8, so this will round to 0.1237. Okay, that's how that one goes. Okay, let's bring us back to our slideshow. This is our slideshow. And let's take a look at example 8. And this is what we have. In its first 10 years, a mutual fund produced an average annual return of 20%. Assume that the money invested in this fund continues to earn 20% compounded annually. How long will it take money invested in this fund to double? So we are once again dealing with compound interest. And if that's the case, our equation is A is equal to P times 1 plus R divided by M raised to the M times T power, where T is time. Now, what do we have? We know that the fund is going to earn 20%. That is R. That means R is 20%, which as a decimal is going to be 20 divided by 100, or 0.2. We are compounding annually, once per year, and that means that M is equal to 1. Now, here's the part that we need to pay attention to. We want to know how long it's going to take. How long will it take? That means we are looking for T. You want to know what T is. And we want to know how long it's going to take for the money to double. So that means that it doubles when A, your future value, is equal to twice times the present value. So with all that in mind, we are going to have 2P, that's what A is equal to P times 1 plus 0.2 divided by M, which is 1, all that raised to the T power. All right. Now, notice that I have a P here and a P here. They cancel out. If I divided by both sides by P, they would be gone. Okay, 0.2 divided by 1, well, that's just 0.2. Okay, so I could write this as 1 plus 0.2. So my equation then reduces to 2 is equal to 1.2 raised to the T power. And T is what we are looking for. Okay, now we have T in the exponent, and we need to get T out of the exponent. And the way we can do that is by taking the common logarithm, or the natural logarithm, it doesn't particularly matter, of both sides. It's just if you're going to use one on one side, you got to use the same one on the other side. So we're going to stick with the common log. So that means we're going to have log base 10 of 2 is equal to log base 10 of 1.2 to the T power. Now we can apply the power property and rewrite the right-hand side as t times log base 1.2. And over here, we still have the log base 2. Now we can divide both sides by the common log of 1.2. Okay, these cancel, and we have that t is equal to the common log of 2 divided by the common log of 1.2. And that is going to be equal to, let me bring my calculator up, the log of 2 divided by the log of 1.2. And that gives me 3.8017. And I think we can just round to 1/10 of a year, so this is going to be approximately 3.8 years. And then finally, how many years will it take $8,000 to grow to $16,000 if it is invested at 12% at the following compound rates? So once again, we are looking for T. This is our interest rate, R. As a percentage, we want to know what it is as a decimal. And we are going to be looking at a quarterly compounding rate when m is equal to 12, m is equal to 4. And they're going to be looking at continuous compounding where P is, or your future value is equal to your present value times e to the RT. So for this problem, we have regular compound interest. And the equation for that is the future value is equal to the present value times 1 plus r over m raised to the mt power. Okay, in this particular case, m is equal to 4 because we're doing quarterly, which means it's 4 times per year. And r is equal to 12% divided by 100, which is equal to 0.12. So, and then of course we have that A is $16,000. Well, A is $16,000, and P is $8,000. Okay, so making the substitutions, we have that A, we have 16,000 for A. That's going to be equal to 8,000 for P. 1 plus 0.12 for R divided by 4 for M, and that's going to be raised to the 4 times T power. And once again, we are solving for T, which means it's going to involve a logarithm. Okay, there are a couple of simplifications that we can make. Okay, the first one is that 0.12 divided by 4, that happens to be equal to 0.3. So we can write this as, or 0.03, I'm sorry, 8,000 times 1 plus 0.03 raised to the 4t power. We can take that one step further and say that we have 16,000 is equal to 8,000 times 1.03 raised to the 4t power. We can now divide both sides by 8,000. And if we do, these will cancel. This becomes equal to 2. And we will have that 2 is equal to 1.03 raised to the 4t power. We can now take the logarithm of both sides. And if we do, we will have the log of 2. And this is the common log. It's going to be equal to the common log of 1.03 raised to the 4t power. Using the power property, we will have that the log of 2 is equal to 4 times t times the common log of 1.03. We can now divide both sides of the equation by 4 times the common log of 1.03. If we do these cancel, and we have that t is equal to the log of 2 divided by 4 times the log of 1.03. Computing that, we would do it as follows. And once again, we have to be a little careful because we have 2 terms in the denominator. So that's going to be the log of 2 divided by parenthesis 4 times the log, no, that's not it, log 1.03, close parenthesis, close the other one, hit enter. And here this is what we have. We will have that t is equal to 5.86 years. Which I guess we could say rounds to 5.9 years. Okay, now for the continuous compounding case, we're going to use this particular equation. Let me change colors so it doesn't get too confusing. All right, so we have that r is still 0.12. And since we're doing continuous compounding, we have this. It's a much simpler equation, thank goodness. So we're going to have a, which is 16,000. Is equal to 8,000 times e to the 0.12 t, and we are solving for t. First thing we can do is you can divide both sides by $8,000, or by 8,000. These cancel, and then we will have that, and this is equal to 2. 2 is equal to e to the 0.12 t. Now in this particular case, since we have a term with Euler's number in it, we want to take the natural log of both sides. Okay, you can take the common log of both sides, but it gets a little complicated. It's a lot easier if you take the natural log. So whenever you see something with an e raised to something, you think natural log. So if you do, you will have the natural log of 2 is equal to the natural log of e to the 0.12 t. Using the power property, we will have the natural log of 2 is equal to 0.12 t times the natural log of e. And what is the natural log of e? The natural log of e is equal to 1. So we are left with the natural log of 2 being equal to 0.12 t. Divide both sides by 0.12. Okay, that should be a 1. These will cancel, and we have that t is equal to the natural log of 2 divided by 0.12. Okay, and what is that going to be? Well, let's figure that out. Natural log, ln, 2, close parenthesis, divide that by 0.12, and we get 5.776 years. Let's make that 5.77, and that would round to about 5. Well, I forgot my 7 there. 5.8. And that is all that I have for this particular video. Notice that this video covers both parts of section 2.6. That's why it's a little long. If you have any questions, please feel free to contact me. And this is Bob Oil, signing off.